Good evening to everybody. Now I am going to give a small introduction about spectroscopy and mainly about the classification of molecules. What is meant by spectroscopy? Spectroscopy means the interaction of matter with light. We will study the spectrum, how the spectrum we get means the interaction of matter with light. Okay? And in that particularly I am going to give a small introduction about the rotation of molecules. Spectroscopy in the microwave region is concerned with the rotation of molecules. I am going to explain how the microwave region is concerned with the study of rotating molecules. You would have already studied about the rotating molecules in your UG classes. But I have to say how the microwave region is concerned with the rotating molecules. The rotating molecules, you know the molecules will rotate like this, and there are different types of rotation in different directions, and the rotation frequency, I am repeating again, the rotational frequency is related, comes under microwave region. Can you understand? The rotational frequency falls in the microwave region. So, the microwave region is concerned with the study of rotating molecules. The vibration and the frequency falls under the microwave region. And then for vibrational spectroscopy, it falls under infrared. Okay? How the vibrational frequency falls under infrared. So, if we incident a microwave light on a rotating molecule, it will react to that molecule. So, how it will react? The dipole moment will change. What is my dipole moment? Two charges separated by a distance. The molecules will have two different polar charges. Though they will separated by a distance and they will exhibit a dipole moment. When you incident a microwave light on a rotating molecule, the dipole moment will change. How the dipole moment will change? The magnitude or the distance will change. For example, the rotating molecule will rotate like this. During rotation, the distance between the molecules will change. Okay? Or the direction will change. Dipole moment is a vector. Okay? So, it will change in magnitude or it will change in direction. Sometimes the distance will change, sometimes the direction will change. Anyhow, the dipole moment is changing. So, a molecule to be microwave active, what is the condition? The dipole moment should change. And next, the rotation of three-dimensional body will be quite complex. So, we are concerning about the two-dimensional rotating molecules. For two-dimensional rotating molecules, when we have to study about the rotational, we have to concern about the moment of inertia. What is the moment of inertia? It is the quantity of torque. Okay, it is the quantity of torque to be given to a molecule to rotate along a particular axis. So, we classified the rotational component into the three rotational components, three moment of inertia components should be taken into account to study the rotation of molecules. First one, rotation along some one axis. It is denoted as IA, and next it is denoted as IB, and next it is denoted as IC. Okay. For example, IA is designated along the bond axis. There are two molecules. Okay. IA is designated along the bond axis, and next axis is along the perpendicular IB, and next one along the crosswise IC. Three perpendicular components. And I have explained how why we are concerning the moment of inertia. It is the quantity of torque to accelerate along a particular axis. So, only we are concerning about the moment of inertia. Okay. First, we are going to see about the classification is based upon the moment of inertia. First classification is linear molecules. And you know atoms are arranged in a straight line, example HCl or OCS. And there are three different the rotation for linear molecule. One about the bond axis. The bond axis, the bond which joins the two atoms or two molecules along the bond axis. And another one, rotation along the end over end rotation and out of the plane of the paper. This one and this one, okay. And in this, Ia is equal to 0. Do you know why Ia is equal to 0? Rotation along the bond axis 0. Do you know? Anyone? Can anybody say why Ia is equal to 0? Rotation about the bond axis need a huge energy, okay. Rotation about the bond axis need huge energy, okay, because moment of inertia is the torque to accelerate along a rotational axis. This need huge energy. Along the bond axis it needs huge energy. There is rotation, but it is ignorable. We are ignoring that. So, it is taken as Ia is equal to 0. And next one, symmetric top. And symmetric top molecule, you know the examples I have given. Here we cannot neglect moment of inertia along the A direction, okay, because three massive atoms are concerned here. Three massive atoms, three atoms. So, three masses are concerned here, so we cannot neglect that. So, Ia not equal to 0 and IB is equal to IC, okay. And next, spherical top. Spherical top, when a molecule has three moment of inertia, all the three moment of inertia are identical. Above all the types of molecule, this one has the highest symmetrical one, linear or symmetric or symmetric, okay. The spherical top is the best symmetrical molecule, okay. And next, in this three moment of inertia are equal, okay. And next one, asymmetric top molecule. These molecules, the majority they are different. The moment of inertia are all different here, okay. And these are the pictures for different classification of molecules, okay.